All right, let's, you probably remember where we ended last time. If not, this is the thing we ran last time, the sort bench, there was sorting, all kinds of things. So anyway, let me just give you a correction for something I said. In the last class, I repeatedly drew this B tree node with 2 pointers in it. It actually has 3 pointers in it. Well, not
red,
B tree,
black
sorry.
tree
Red, black tree, red, black tree.
A parent pointer?
Yes, it has a pointer to the parent because otherwise implementing an iterator is really hard. So I didn't write it, you know, and so whatever. So that is what explains the fact that the set degrades much faster than a doubly linked list because it is just taking up more space. So anyway, that clears up that. Let's move on to what we are going to do today. So, so today we want to look at memory in a somewhat more systematic fashion to try to see what's going on. You know, and maybe we can, you know, understand what's going on. Maybe not. We'll find out. So the
Let me
next.
talk for a little while. I cannot resist.
He cannot resist himself.
I cannot resist. Before one can understand anything, one needs to know, right? That is, unless you find some data, you cannot understand it. So one thing which we are trying to convey, it's important to try to find data. It's important to get into the habit of measurement. Whatever we are with, if we think we are scientists, we have to measure. If we think we are engineers, and our titles contain word engineer, we have to measure. Measurement is an essential part of what we do. By the way, understanding is not always required, right? Because very often it's too hard to understand. What we will see and what I discover, that we have to deal with very complicated systems. And anyone who tells you that he fully understands what computer is doing is either delusional or a liar. A modern computer is a very complicated thing. The only way you could get some sense is by sort of experimentally poking and getting data. And by the way, you say, oh, that's unfortunate. Well, think about doctors. What do? Do they understand how our bodies work? No, of course not. Anybody who had any serious disease knows that doctors, you know, they measure, they have protocol. They don't understand.
They have some incomplete theories, but they know that these are incomplete theories. This is a correlation we have observed. And
actually, in case of doctors, no, they don't have any incomplete theories. They say there is this poison, and if we put some amount of it into Jerry, he might recover. And how it happens, they do not know. I mean, all the cancer treatments are based on this just simple fact that, you know, if you take some shoe polish, dissolve it in water, and pour it into Jerry, maybe some of the cancer cells are going to be killed. Right? They together with some other, and they will also, they call it multi-modal treatment. So first they'll cut a part of Jerry, then they'll pour some poison into him, and they'll radiate him just in case. And they say, well, with certain probability, he will not die. And in many respects, it works. Modern medicine is a very successful sort of branch of science, precisely because they use these statistical techniques without fully understanding them, right? And we have to acquire certain humility and sort of say, yeah, we don't understand. We do not understand why this algorithm is better than this algorithm, with this data structure, with this processor running on this compiler. Think about the complexity of the thing involved. I mean, there is a processor which is beyond belief how complicated it is. We were just looking at the number. I mean, a modern CPU has 2.5 or 3 billion gates. Transistors, pardon me. You cannot possibly understand things with billions of parts. And again, somebody will say, well, but most of it is cache. True, but it's still
but the remaining billion is a lot, you know. And fine, there are 4 cores, but you know, 250 million is a lot as well. So.
Right. So it's enormous amount of very complicated stuff, which is doing something. People who design it are very good engineers, but there are about 1,000 of them. And they don't talk to each other. I mean, it's impossible for 1,000 people to talk to each other. So nobody actually knows what the processor is doing. Then there is a bunch of compiler guys who, theoretically speaking, talk to these architecture people. But no, guys. I used to be part of compiler and architecture organization. Some of you might have heard of MIPS. You know, I spent 5 years sitting in the building with architects and compiler people. And occasionally they have beer together, but they don't really understand what is going on. That is, architecture people do not understand compilers, compiler people do not understand architecture people, because it's very, very complicated. By the way, when we talk about compiler people, we have to understand that there are these layers of compiler people. There are people who do software pipelining, who have absolutely no idea about how global optimizer works. And then there are front-end people who know nothing about any of this stuff. They deal with languages. And then there are some idiots who write libraries, which you use. So, you know, it's very complicated, right? So you have this very elaborate edifice with many, many people responsible for it. And you're sitting on top of it, building your application. So one thing you need to get to it, you have to experiment. You have to learn to do measurements, poke things, try to see what happens if you sort of move things a little bit here and there. It should become a habit. Right? Sorry.
And data absolutely takes precedence over theory because it's...
Yes, theoretically it's a good data structure. Okay?
But if it's not fast,
so maybe you could publish
fast, you know.
But it will not work in practice. Yes? So no data structure is good unless you measured it.
If the map disagrees with the terrain.
Yeah, I mean,
the terrain.
Believe the terrain, yes. That's what Google says when you use Google Map. You know, recently we went to have, we had lunch with Benoit Paramandai. And we went to an Indian restaurant, which is located in a certain mall. And both Google Map and Apple Map located it on a different side of the mall than where it was. So, you know, fortunately we knew where it was, so we didn't believe the map. But, you know, it happens. We have to, so what I'm trying to say that this is this very important thing of measurement should become a habit. Sorry, Param. Which map was wrong? Both were wrong, and by roughly equivalent distance, but they were very wrong. On average, they would be more wrong. So you would get even further away if you average. Now, of course, you realize how funny it was in case of Benoit. That's the guy who is going to work on maps. So he promised that that is going to be the first thing he will do, like after he joins Apple. So you know, we will ask him next time.
Yes.
Or we could check.
We can always go out for lunch again sometime.
Yes.
And who knows, someday, you know, maybe the restaurant moves and then, you know, the map will be correct.
Yes.
So anyway, let's try to measure something simpler, right? This was what we had before was too complicated. So I'm going to show you a much simpler kind of benchmark. This thing is called iters. Okay, so since we were talking about node-based data structures, let's just take a linked list and try to iterate over it, and then we'll see what happens, right? Okay. So it's the usual thing we did with all of our benchmarks. We have a min size and a max size for the type of data structure we're going to construct, and in our main loop, we are going to measure three things, right? We are going to measure how long it takes to iterate over a vector of the same size, and then we are going to iterate over a list and a forward list. Okay? And there's one more twist in the whole thing, which is that we are going to iterate over the list twice. Once, we are going to iterate over an unshuffled version of the list. So that's something that we allocate in order. It's laid out in memory in one after another. We iterate over that, and then we shuffle it by sorting it using merge sort, and then we iterate over it. Right? And we see what the difference is. And as usual, we'll report our time per element. Right? So the rest of it is pretty straightforward. I'm not going to go through it. One other thing worth pointing out is if you were to write a simple loop that says, oh, let's for I from first to last, let's just iterate over the list, the compiler is probably going to optimize it out. You have to actually be, I think I wrote versions of this that reported 0. So what we are actually doing, just to be clear, is that we have a source and we are copying numbers into the destination list. And that, for all practical purposes, gives us the same behavior as if you were to iterate over the list and do something with it. All right, let's try it. All right. So first, let's look at the vector column. And this is something you've probably seen, the typical way of, yeah. Right, so before we start, we construct the max size is what? We construct a vector of the maximum size and fill it with random numbers. That turns out to be a pretty expensive operation, and we don't want to do it repeatedly at the larger sizes. So we do it once and then use sections of that for the rest of the runs.
And what about the destination? How is that?
It is allocated by simply creating a list and initializing it with two iterators, the begin and the end. So I just define, std list of double f comma l. That's how it's allocated. So whatever the library is doing by calling malloc, whatever malloc gives us. In practice, we have observed that if you start from scratch, you have no memory allocated, you will get nodes in sequential order. Unless you're using the default malloc on Linux, in which case you will get whatever, but in general.
For the destination.
Oh, for the destination of the copy, let's take a look at the code. I suspect we'll find out. First, last, begin test container. Right, so we construct the test container using first, last, and then we copy into it again. And what we time is the second copy.
I think we need to look at the numbers.
Yes. All right. So let's look at numbers. Well, so the first column here is the list when we access it sequentially. And you can see when you're in your L1 cache, of course, the vector is fast. The list is slower than the vector, but it's still fast. And even when your list becomes pretty big, it doesn't degrade very much, even though at this point it's in memory. It's it's not in cache. It's still pretty good. However, if you take the same list and you sort it, and then you iterate over it, that is very dramatically different. And by dramatically, I mean 10x or more. Right? So you're writing your application, you test it out with a small data set, you run it with a big data set, you may get into trouble. Or you run a test where, let's say you do try it out with a big data set, but the list never gets shuffled enough, you still get into trouble. So, if you're actually, well, if you are using a list, you certainly want to make sure, you want to be aware that you could get a difference in performance of 10x or more, depending on what the exact situation
Actually,
you're in.
this is 25x compared with unshuffled list. But it is
100.
100x, 2 orders of magnitude, compared with a vector. Iterating through a sort of list which was, shuffled around, could be 100 times 2 orders of magnitude. That is something. Sorry, again, I interrupt. But you were sort of saying 10x. Param always wants to be fair. I don't want to be fair. I want to shock you. It could be 100 times compared with the sort of what you would expect if you iterate from an array. 100 times is a lot. It's a second versus a minute, simply speaking. People might be prepared to wait 1 second to get a result. But a minute, especially if you're waiting in front of the computer for a query, is not something people will accept. It is really very slow. Right?
It's the difference between something that runs in 1 hour versus something that takes 100 hours, which is multiple days. Right? So even if you were doing a batch job, this kind of multiplier is something, that is not a joke.
And these are not such enormous numbers. If you go down, this is not even big data as big data goes nowadays. What's 16 million? Nothing.
The other column shows the same thing for forward lists, and really the only difference between them is that the curves start going up a little later. The forward list takes less time, less space in memory, so it starts degrading a little later than the main list, but that's pretty much it. But in terms of overall behavior, you see very similar multipliers. This is something you have to be aware of. So this shows us that indeed non-local memory references are bad, and particularly when you're dealing with linked data structures. You don't control your malloc typically, and when you're designing your application, you have to consider this. Okay, so let's move on. We have another little benchmark that again illustrates the kind of trouble you can run into with a node-based data structure if you're not careful, right? So here we were iterating over lists. Let's instead look at sets and hashes, right? So we have this in terms of code is maybe even simpler, right?
So, Param,
Yes.
one thing that occurs to me is, in looking at this, is you could easily find yourself in a situation where you've developed something and you did test it, and you timed it, and you said, look, this isn't so bad. Well, you may not be aware that the reason it's not so bad is because the data you're getting is in a nice order, and you don't take that into account.
Yeah.
And then what happens is, a change happens to the system that's completely unrelated to your submodule. The user is giving you data that's in the same form, it's the same data structure, but it's now shuffled, and you see this incredible, cratering of your performance without realizing what happened at all. And even after you tested it, even after you said, well, let's see what this does in the real world, and you say, oh, it's not so bad.
This is something you have to be aware of during testing. You have to know that when you're testing, if you have a node-based data structure, you need to test what happens when I get data in a different order, what happens if my application runs for a long time and therefore my heap is fragmented. So for instance, if you were to run this on Linux with the default memory allocator, what you would see is that even the unshuffled line becomes really bad towards the end. And why is that? Because what we are doing is we construct a list, we free it, we construct another list, we free it, we construct another list, we free it, and what we end up with is actually a memory allocator. Well, that memory allocator does no longer gives us things in order at that point, right? And this is very, very memory allocator specific. On the Mac, you do this test, you do get things in order. On Linux, you don't. On Linux with tcmalloc, you do. And who knows? I mean, are you tracking changes to your memory allocator? You know, this is something that you have to be aware of when using node-based rate structures. There's no simple answer to this.
Okay, one more interruption. This is, of course, anything I say does not relate to subject. It's just general ravings. But the general raving at this point is that we already talked about necessity of testing and writing unit tests. Profound original idea. But another profound original idea, you have to have unit measurements, right? That is, the sad fact is that for most things, even such things as the standard library, there are no standard unit measurements. When I developed it, they existed. But I made a dramatic mistake when I released STL into the public domain. I didn't bother to release either tests or measurement suites. I could have. I was a manager in charge. I signed the thing and would have. I didn't do it. Eventually, we retrieved them and they could be found, but they sort of obsolete. They no longer work. They sort of not related. I should have sort of insisted that it comes as a whole thing, that there are algorithms, data structures, corresponding tests, corresponding measurement, and as a matter of fact, there was also corresponding visual simulation thing, which was quite useful, at least for me. But it did not happen. And therefore, performance often again, it's easier for me to talk about something I know well, about STL. Over several times, the performance of STL for some particular sort of egregious cases was, say, Microsoft version of STL. On several occasions, there were dramatic performance sort of degradations. How would they come? Well, not improvements. I mean, what happened is that they would sort of come up with some brilliant ideas. This is a common idea. Let us replace all pointers with wrapped pointers because, you heard pointers are evil. We'll make all iterators safe iterators without measuring performance. So at some point in about, say, 8 years ago, everybody at Adobe started doing the following thing. They'll get a vector, you know what a vector is, yes? They'll get begin and end. And then they will use star ampersand to get the pointers. Because if they use iterators, performance was not sufficient. Then they discovered that Microsoft compiler would not compile it because star ampersand with and is actually illegal. Anybody knows why? You cannot dereference and, And while you effectively can, it still doesn't matter. Those of you who know the stuff could figure out. But people started writing horrendously complicated macros. So what happened that somebody at Microsoft decided to improve the stuff but not measure the performance. Right? So it has to become a habit for all of us to think in terms of providing some kind of unit measurement for, again, you say, well, but I don't do performance critical stuff. Well, maybe then you don't need it. But even there, I would argue, because even if you write something in Python, it might still be important to measure how long it takes, because something like what John describes might happen. The data might change. You get data in order, then data starts coming randomly shuffled. Or the other way around, by the way. Sometimes randomly shuffled is very good, and coming in order is pretty bad. So whichever way things change, it would be nice to have measurement tests again.
And the best time to do it, just like we all know the best time to write tests is when you write the code, because you need to test it anyway. Doing it later is just less effective. Similarly, if you're writing something that is performance sensitive, you are going to be testing performance anyway. You need to test all of these cases. If you do it manually, you're throwing away that work. You have to, if you write those tests, you can do it repeatedly. If you make your own modifications, you can run them easily. It just makes sense to do it.
But there's a difference between unit measurements and unit tests, and that unit tests could be run automatically, and you can easily set up verification rules or whatever, whereas the measurements depend on the platform, on the type of hardware.
No. There is a very simple technique. You watch for regressions. It's basically, this is, for example, was commonly done in the SGI compiler organization where I worked. They would watch sort of the performance metrics for the compiler daily. And if there was a regression, managers would start running around screaming. Right? So if you didn't know, it wasn't correctness, it was very, very simple thing. Whatever you check, if you have a check-in, there shouldn't be performance regressions. Or at least, if there is, you have to explain it. If it's a major one, it's a big issue. Right? So you could automate it very, again, this is, it's a different thing, but it's, you have to keep track of the stuff and then compare it with.
Another thing you can do is you can have a baseline. So you can say, okay, this operation, let's say, I don't know, iterating over a vector is such and such, and therefore these other operations should be comparable to that in some sense with some multiplier. Or even if you don't have anything automatic, something that runs a set of tests that are desirable and prints out a table that like we've been doing, that is better than not having them at all, because you can then someone who makes a change can run them and at least visually inspect it.
But performance regression is an old, well understood technique. Sort of you're not trying to sort of be profound, you're just saying, well, we do not want performance go down, and whatever we run after every change, we want these numbers to go down, not up. Yes? It's not, and you say, well, it does not guarantee, it guarantees enough in the sense that, you're at least measuring something, which sadly enough, many organizations, I don't want to point fingers, do not do. Right?
So, the second thing we're going to show you is, it's very similar. This time what we're going to do is we're going to create a set and an unordered set. And we'll take the vector, and then we will add all of that's in the vector into the set, and then iterate over the set. Right? So if you look at our time container function, what does it do? Okay. We create this container from our vector, and then we iterate over the entire container, copying stuff into a vector, right? And we time that. Then we make a copy of that container using the copy constructor, and we do it again. That's it. There is nothing else here. Okay?
What's the point of the copy?
We will find out. So what is the point of the copy?
Now you're
When we had created the first version, we had the array in random order. So you got some tree that you allocated nodes in whatever order, right? Apparently, when we made a copy, we ended up with something that was just somehow much more linear in memory, and it was good for iterating over. And
So the point is you should always copy your sets before you use them.
maybe
not a bad thing to do.
if you're
Yes,
creating
that's
it
what
once
tells you.
and then you're using it lots of times later, this might be something worth considering. And the amazing thing is it doesn't just work on sets, it works on hash tables as well, again by, over 10x, very, very dramatically, yes. So if you're using a linked data structure of any sort, I mean, you see things like this. You have to be very aware of this if you're using these things.
And again, what you suggest, just doing a copy, is often a very nice optimization.
In a case where you're building an index to something that's going to be queried a lot, so your build time is amortized over
Yes.
many requests.
Yeah.
Makes a lot
Copy
of
is
sense.
fast,
Yes.
relatively speaking. Yes.
Yeah, it's fast, it's easy. Okay, I am going to kill this here because I think it has
Yeah,
already
you
shown
killed
us
it,
everything that it was going to show us. So just before we end this sequence of benchmarks, I mean, these are not data structures that you should be iterating over anyway, right? I mean, if you need to iterate, this is what you need to do. If you need to, because I mean, this is, in some sense, we are testing it out of what it was really designed for. But I mean, sometimes you do iterate over sets, so you have to be aware of this. But if what you're doing is iterating over something, this is what, I mean, if for instance you create a set and you never modify it, just make a list and sort it, and then you can do whatever you want with it. Right? This is what you want to do.
Not a list, not a list.
Make a vector. When I say list, I mean, I'm not a C++ guy, in other words, right?
Neither
Yes.
he's a data structure guy.
But what you mentioned here is only correct for C++, right? It may be true or may not be true if we use other implementation languages.
The bottom line.
No. This is an amazing question. Why do you think it relates to C++ at all?
Because as you showed in a previous lecture, one before, that using complicated data structure in Python may be actually beneficial. So same in Java, we don't know if the first set allocation may be contiguous and not contiguous in memory. We need to measure, as you said.
No. But the data structures tend to be like Java uses red-black trees, which are fundamentally identical to C++.
But whatever you say that the copy is going to help, it may or may not be true in Java.
Well, it will be true in Java. Of course it will be true in Java.
Well, depends on the
unless
properties.
their implementation sucks. Because if you allocate things sequentially, again, let's go to the simpler case, the case which we did before, that shuffle list is slower for the iteration than a freshly allocated list, yes? It is true in C++, Java, Python, Ruby, Prolog, whatever. Why? Because freshly allocated list, you allocate 1, 1, 1, 1. If it's shuffled, That's the whole, it's an algorithmic issue. It has nothing to do with languages.
The unfortunate part is that memory allocators typically give you no guarantees whatsoever about what they are giving you. Right? So that is true, but this is not about C++. This is about a vector versus a tree versus a hash table. They may be implemented in whatever.
Now you were speaking set and hash, right?
Yes.
So copying a set gives you a boost of what?
10x.
A magnitude, right?
Yes.
Over freshly allocated set. So what I'm saying is that there is some memory optimization that happens. It may or may not be true in Java.
Well,
No, you have to measure, absolutely.
you have to measure, but it's nothing, it's not the language. I mean, the fact that you use C++ here is utterly irrelevant.
And the point is, whatever language you're
Okay,
using, you have to figure out a
we
way
have to
to
go
trick
to
it
the-
into doing what you want it to do, ultimately.
Going back to the beginning of this course, languages do not matter, okay? I know that none of you believe it, but I repeat, languages do not matter. Unless you know what you're doing in terms of data structures, you're going to write nonsensical, slow, and bad code, okay? There are all these battles like Camille comes and says, oh, Java is my, it's nonsense. It's nonsense. It's not because, it's just, it doesn't matter what you use. You have to figure out the fundamental data structures. and then implement them somehow in your language. If you start relying on the language, you start writing all the, I don't know what you could write. You write, I mean, yes, I know what you write. I actually, not you particularly, but I read many people code. And it often shows profound misunderstanding of what is going on. Okay? When people use STL, it's not, I mean, you know, I would be one of the people advocating, you know, total ban of STL at A9. Why? It's not because STL is bad, but because people need to understand data structures. Otherwise, they do horrendous things. It's not because it's in C++, it's not because it's at STL, but if you do not understand what data structure is doing, you're doomed. And since STL allows you in one line to create extremely complicated and slow data structures, you know, it enables very bad programming. You know, I pull my hair. Why did I create this monster? But I never intended people to program without understanding. That was not, I mean, you know, it's like you don't give children sharp knives because they'll cut their body parts. Nothing you could do about it. I mean, they're children. But I thought when working on STL that I was dealing with grown-ups. I was wrong. I mean, I'm criticizing, I'm allowed to criticize my own work, right? So, you know, giving people powerful data structures without demanding that they understand them is irresponsible. It has to come with a warning that unless you understand how this data structure works, do not use it. It should come with any data structure, come with any algorithm. Or at least professional programmers should not be allowed to use something they do not understand. But that, I mean, no here, no there. So no, I do not believe that we're talking about languages at all. This is the whole point of this course. It's nothing here is about C++. Yes, we use C++. But yes, I could write similar benchmark in Java. Remember, we started with actually writing the similar code in Java and C++, basically showing equivalence.
A tree in any language is a heap allocated bunch of nodes connected by pointers. And they're all stored in memory. Depending on where they are, they're going to behave the way the processor behaves with that data structure. There's nothing you can do about it. But you have to understand your platform enough to be able to map from what you're writing to what's going on in the machine. If you care about a 10x performance difference, which you almost always do.
Or 100x.
Or 100x. Right. All right.
So,
Yes.
Just something you said in passing just a second ago is what you said. Of course, if you're going to iterate over this, you wouldn't use set at all. You would use vector. But if you're not planning to iterate over it, there's no reason to use set over unordered set, right?
Let's find out.
Set, right?
Let's find out. I have another benchmark for that.
No. You see, sometimes people need to get things, for example, if people want to have things known as set operations. Some of you might have heard of intersection. You know, like infra does intersection. You might not be aware, but it is in there, right? So if you want to do set operations, sets are much more effective. Huh? No, then unordered sets. They're much more effective. Set operations are very good on ordered sets. Yes? Because you could just do very simple, naive, but extremely fast algorithms, which you cannot do in other cases. Again, sort of what Param was saying, we should be eating, was that set provides iterators. Hash set provides, or whatever you guys call it nowadays, unordered set. Standard committee. Huh? It is a hash set. So they have iterators. but these things were not designed to be this is not their primary thing. Like, you could insert in the middle of a vector, but it's not particularly designed for that. Right? You could iterate through a set, but it's not designed for that. It's designed for fast find and fast insert. So you have to understand these trade-offs. Even all the operations, like for traversal, are provided. They're normal iterators on all these things. They're not particularly optimal. I mean, all the data structures have trade-offs. That's the point. And this benchmark, what Pranam is saying, is not telling you to use this or that. By the way, whenever you might not fully understand what we're trying to say. For example, I tell you, do not use node-based data structures. That's an exaggeration. What I'm telling you that you should always consider array first. But sometimes you need to use node-based data structures because your task demands it. Is gratuitous use of complicated data structures for simple tasks is what is unacceptable. Yes, sometimes you need to use lists. But you have to, again, people have to put considerable amount of time into choosing data structures, even if, again, the problem with STL, that it's actually easier to use set than a vector. It's 3 letters versus 5. And we know that programmers optimize the number of keystrokes. This is why we have these wonderful commands like cat versus concatenate, or unique spelled in a rather un-English way, so minimizing keystrokes. So people use set without thinking. And that is, it's again, you don't need to think about C++ sets. You need to think about red-black trees. You need to know how they work. Again, the thing which I hear time and time again, I remember I was visiting one university and, there was this argument. People were saying, well, now you sort of abolished algorithms and data structure courses. People no longer need to know. They could just use. And I said, no, absolutely not. They need to know more now because now they can use. The assumption now, like 30 years ago, people didn't need to know about red-black trees because most people couldn't implement them, therefore they just, but now you have to understand how they work. You really have to understand the complexity trade-offs because they are available. So it's and do not believe anyone who says there is this simple recipe or it's language dependent. There are no simple recipes, and data structures do not depend on the language. They do not. Knuth intentionally rejected the idea of using a programming language. Again, if you read the introduction to the first volume of Knuth, he discusses that, languages come and go, they're fashionable languages, they change every 3 years. That's what he writes. He wrote it in 1968, and I don't think it changed that much. Therefore, he says, I'm going to implement my algorithm in mix. We could argue about whether that was a wise choice or not, but he is right in one fundamental sense. He's right in many, many ways, but in that sense, it's not about programming languages. This is why he describes data structures with pictures, not with, sorry. I mean, you just stepped on a toe which hurts. I mean, I'm trying to teach something, and the summary of it, it's not about languages. So when I hear somebody saying, oh, but you're talking about C++, I get mad. Because I was trying to send a very clear message. And the message, it's not about C++. Okay, let's go with it.